Good morning, everybody. Not good morning, sorry. Good afternoon, everybody. Uh, Thanks for tuning in. Today, we are delighted to have Aghil for the seminar. Aghil is going to talk about positivity of static quasi-local mass in general relativity. So take it away, Aghil.
Thank you so much, Pascal, for the invitation, and thank you everyone for joining the talk. Today I want to talk about positivity of a static quasi-local mass, and I should say that this is a joint work with Marcus Curry and Professor Yau. So let's just try to give you the outline of my talk. So I'm going to start with the framework of GR and definition of quasi-local mass in GR. Then I will try to briefly say what is the definition of quasi-local mass with respect to static reference, and I call that like static quasi-local mass in this talk. And at the end, I will state our main results, which is the positivity of a static quasi-local mass with respect to AdS Schwarzschild references. And I will give you a sketch of the proof to have a general idea how we prove these statements. So I'm not going to go deep in the details, but I hope that at the end of the talk, you have an idea how we actually, because we are using different tools and to achieve our goal. Okay. Let's just start from the beginning, and the beginning is like Einstein equation, Einstein constraint equation. So as we know, general relativity is a geometric theory of gravitation, and we are studying like Lorentzian manifold in GR, which are solutions of the Einstein equation. But in many problems in GR, we don't need to know the knowledge of the entire space-time. So we can just study the initial value problem. So that is, you look at the space-time and you fillet your space-time by space-like leaves, like this picture over here. And you will have, through this fillation, you will have a triple, we call that initial data set of the Einstein field equation. And one is the manifold. We tell you what is the shape of the manifold. G is how you measure the geometry or the metric lengths and angles and curvature. And also K here is the second fundamental form, which tell you how actually this initial data set is sitting in the ambient space. So it will give you information about the ambient space. Note that using the Gauss-Codazzi equation, we call the initial data set of Einstein equation if it's a solution of these two equations. One equation is a scalar equation, it's called the Hamiltonian equation. Another one, it's called the momentum, equation, momentum constraint equation, and it's a vector equation. So the right-hand side of the Hamiltonian, equation, or constraint equation, we have a scalar curvature, the norm of the second fundamental form, the trace of the second fundamental form square, and the cosmological constant. And on the left-hand side, we will have like energy density of the matter field in the space-time. And the other equation, the left-hand side, we will have the energy flux, and the right-hand side is a dive of a tensor in terms of second fundamental form and the trace of second fundamental form, which comes from the trace of the Codazzi equation. Note that the left-hand side, we have a kappa, which is a physical constant. And in this talk, we are assuming like a geometric unit. So G and C are 1. So kappa is just 8 pi. Okay, so this is an initial data set, but initial data set will be relevant physically if we impose some energy condition. And the energy condition that we are going to use in this talk and in many problems in geometric analysis and mathematical GR is the dominant energy condition that says the energy density is actually bigger than equal the norm of J. Okay, so let's go to the quasi-local mass. What is a quasi-local mass in GR? So the problem with the GR is like there is no density for gravitational field. So as we know, for any Riemannian or semi-Riemannian or Lorentzian manifold, at each point you can define a normal coordinate, and that normal coordinate will make the metric to be the same as Euclidean metric or Lorentzian, the Minkowski metric. So this will translate to a principle in GR, which is the equivalence principle, which says that locally everything looks like the spatial relativity. So there is no density for gravitational field, so we cannot use the classical formula, which is the mass is the integral of the mass density. So what we can do, the next best thing we can do is just try to compute the mass of finite region of a space-time. And we pick a finite, a bounded space-like region. Let's call that omega-3, sitting in the space-time n3 and 1. And you want to define the mass in terms of boundary data. And the boundary data, the intrinsic one is the Gauss curvature, and extrinsic one is the mean curvature vector. So this is really a very fundamental problem in GR. And actually, Penrose in 1982 listed all major, open problems in mathematical GR. And the first one was to define a suitable quasi-local definition for energy momentum in general relativity. So in particular, defining something for quasi-local mass. Note that this kind of problem, like this statement of this problem, is sufficiently vague to leave a room for many different mathematical formations or formulations for this quasi-local mass. In particular, what is a suitable definition for quasi-local mass? So to actually answer this question, we need to go back to physics and try to list our expectation from a quasi-local mass or energy or momentum. And here are some of the expectations that we have. So the first one is some notion of positivity. So we know for asymptotically flat manifold, we have like AdM energy, which is the total energy of asymptotically flat, or asymptotically hyperbolic one, we have like a total energy defined by Crucial and Herzlich and also Wang. So we we prove a positive mass theorem for these spacetime. But what will happen if you have a finite region of a spacetime? So we expect some sort of positivity hold. Okay. The next is like, what will happen if you pick a surface in an asymptotic region? Like, let's pick a coordinated sphere in asymptotically flat, far away, which approaching to infinity. What you expect is whatever is your quasi-local mass, it converges to the total mass. So that's something nice about that quasi-local mass which you're defining. Moreover, if let's say your surface that you're picking, which encloses a domain like omega-3, let's say it encloses a horizon. Then we know from the heuristic argument of Penrose that there is a kind of Penrose inequality for total energy. So a similar kind of expectation can hold for a well-defined or a universal definition of quasi-local mass. Also, you can ask about the stability. So we have stability of the rigidity case. We have a stability result or stability question about rigidity of the asymptotically flat, asymptotically hyperbolic manifold, which says if you have a sequence of manifold, which the total mass it converges to zero, what will happen to the limiting behavior of this sequence? Does it go to the canonical case? Like, let's say in asymptotically flat, does it go to the Euclidean space? In asymptotically, let's say hyperbolic, does it go to hyperbolic space? So this sort of problems has been like raised and studied by many people, including like Christian Sormani, and developed many notions of convergence for a sequence of manifold. So you can add like more properties. Like there is another one by Bartnik, which I'm going to highlight that in my talk. It's about the hoop conjecture. So in one of the paper of Bartnik, which listed all of the like important mathematical problem in MathGR. One of them was like defining the notion of quasi-local mass, which if there are too much energy in a finite region, then you end up with a black hole or a horizon or a mass. As I said, there is no universal definition for quasi-local mass in GR. So the question is, which quasi-local mass enjoy the most of these properties? And that will be a candidate for the best definition of quasi-local mass. So now, how to define this? There is one way to define this, and that is like there are different ways to define this. One of them is like this Hamilton-Jacobi analysis, the same way that they actually apply to define AdM mass and energy and momentum. So Brown and York in 1993 tried to use this method, and actually they defined a Hamiltonian for a physical domain, and then they picked the reference to be Euclidean space. So what do we have in the setting? We have a surface which is sitting in the space-time and enclosing like a space-like region, like omega. The surface is like sigma. This is our surface, and because they assume the gauge curvature is positive, so when the gauge curvature is positive by Weil embedding problem, there is a unique isometric embedding in the Euclidean space. So you have this kind of embedding, so you can compute the mean curvature of your surface in the Euclidean space, and they define the quasi-local mass as a difference of the integral of the mean curvature. And that's end up with this formula, and H0 is the mean curvature of the surface sitting in the Euclidean space, and H is the mean curvature of the surface sitting in the physical space, like here. Okay, so now we can go back to our properties that we listed and ask, okay, which one of them actually hold for this definition of quasi-local mass? So the first one is the positivity. So around like after like 10 years after definition of Brown-York quasi-local mass, Shi and Tam studied this, and what they did, they have like a Riemannian compact Riemannian manifold with non-negative scalar curvature. And they assume the boundary of this domain, so something like this, and the boundary is sigma, and sigma has a positive gauge curvature and positive mean curvature. And positive gauge curvature is you need that for isometric embedding, and positive mean curvature is something technical to solve a parabolic equation. If you have this setting, then they show that actually the Brown-York quasi-local mass is non-negative. And the rigidity happen if and only if it's a Euclidean space. So this beautiful result addresses the positivity. But you can actually go one step further. What you can do, you can ask what will happen if you have a minimal surface or horizon. And actually, this has been like proved in different cases. The case that you have only single component for the horizon, it has been proved by Shi and Tam in 2007. If you have like a multiple components, this has been proved by McCormick and Miao. And if you have a cylindrical end, and then which like asymptotically the surface is going to a minimal surface, then we with collaboration with Marcus Curry and Yao proved this in 2020. Okay. So what else is about the stability? So you can ask question, does it have this Brown-York mass, quasi-local mass, does it have a stability property? So let's say you have a sequence of graphical hypersurface over the Euclidean space, and assume they have a non-negative scalar curvature. And non-negative scalar curvature, I should say, in all of these results, it means you have a dominant energy condition. So the same, you assume the sequence has a positive gauge curvature and positive mean curvature. And now also you assume the Brown-York mass of the boundary of the sequence actually approaching to 0. Then you can prove the sequence actually converges to bounded region in the Euclidean space. And this, we studied this with Cabrera Pacheco, Armando, and also Steve McCormick in 2021. So we proved this This convergence is in flat distance, and you can go to the other norm and ask a similar question that do we have convergence? Okay. What about the hoop one? There is a beautiful result by Shi and Tam. Up to this point, the only like hoop form of conjecture was by the big result, which was a result of Shen and Yau, and that was existence of horizons or mods due to concentration of matter field. And here, Shi and Tam, they actually prove, they try to answer the question of Bartnik and try to prove formation of horizon due to quasi-local mass. So what they did, they pick again a compact Riemannian manifold with non-negative scalar curvature, and they assume the boundary has a positive Gauss curvature and positive mean curvature. Then they define a quantity, they call that m of omega. We call here m of st of omega. And this quantity is actually, you can think of this as a like you pick different, surface, like a surface which enclose a region, like let's say this is my omega. So you pick another one like omega 1. And then you look at the all minimizing Hall with respect to this omega 1, or actually has the minimum area. Anyone has an area larger than this. And you compute the Hawking mass of this guy. And there are infinite options for omega 1, and there are infinite options for like this minimizing Hall as a result. So you take the soup of all the possibility, but you add a constant there, which that constant is a fundamental constant, and you get a definition for mass. This mass, note that it's going inside the domain, so you cannot call that a quasi-local mass, but it's some sort of mass in terms of a Hawking mass of surfaces inside the domain. And then you have this inequality, then they prove that there exists a mods. There exists a horizon, which in this case is a minimal surface. This is a Riemannian setting. And finally, the asymptotic condition. So what would happen if you have a coordinate sphere? What is the behavior of like Born-York quasi-local mass? And the Fan, Shi, and Tam in 2007, they showed that actually it converges to the total AdN mass. So Born-York mass is a very good definition of quasi-local mass, but note that up to here, we are talking about a Riemannian manifold, and we're assuming K is equal to 0. So let's move to the initial data set. So Liu and Yao, they try to extend this definition to the case of initial data set. And their definition of mass is has been studied before by these authors that are listed here. They have a similar definition for quasi-local mass. So this quasi-local mass is, you have an initial data set and you have a boundary which is sigma and with the metric sigma, and you assume again the Gauss curvature is positive. Because the Gauss curvature is positive, you can do isometric embedding inside the Euclidean space, but Euclidean space is sitting inside Minkowski space. So they have some sort of isometric embedding, which is trivial one in the Minkowski space. And based on that, you can look at this time, when you do isometric embedding in the Euclidean space, you have the mean curvature H0. So same as Born-York, you put it, the Hamiltonian is just the integral of H0. And then for the physical case, they put the integral of the norm of the mean curvature vector. So it has information about the mean curvature. It has information about the second fundamental form restricted to the surface. Okay. So there is a problem with this mass. And yes, there's a question, it seems.
Yeah, could I just go ahead and ask a quick question?
Yeah, sure.
Yeah, so what is small sigma over here?
Oh, a small sigma is the metric on this sigma, the boundary.
Oh, okay.
This is the metric.
Okay, thank you.
So the problem with this quasi-local mass is too much positive. And that means it's for many surfaces inside the Minkowski space, it is positive. So this has been demonstrated by Omochada. and others, and Yao tried to fix this by another work with Wang in 2008 and define a general isometric embedding. So this time you don't do isometric embedding inside, like this is R3, which is sitting inside this Minkowski space, which is 3 and 1. For here, they do isometric embedding in the general R3 and 1. So something like this, and they define a height function, and this is the R3, and this is the height function tau, which says the location of this graph. And assuming the height function is admissible, so has some conditions, they put it there, they could prove actually many interesting results about their general quasi-local mass. And they quasi-local mass don't have this kind of problem, which is not too positive. So it's a candidate for the universal definition of quasi-local mass. So let's look at the properties of these. So the first one is the space-time positive mass theorem. So if you have an initial data set, which is a compact initial data set with dominant energy condition, and you assume the boundary has, again, positive ghost curvature, you need that for isometric embedding. And a space-like mean curvature vector, you need that, a technical thing, to show a quasi-linear elliptic PDE has a solution. And if you have these conditions, then you can show that the Liu-Yau quasi-local mass is non-negative. But if it is 0, then that domain is from the Minkowski space. We already highlighted the fact that the reverse is not true. What about the Penrose inequality? As we know, there is no Penrose inequality for total mass in asymptotically flat setting. But there is some result by Curie based on the argument by Herzlich, and that is like proving a Penrose inequality with a constant. So we actually studied this to apply the same technique and prove a similar inequality for Liu-Yau quasi-local mass, and we proved that. So if you have an initial data set which has like outermost mods, and you can have multiple components of these guys, then you can prove that actually there exists a constant independent of the horizon area, such that the following inequality holds. And this is very similar to Penrose inequality. The only difference is alpha. If alpha is 1, then you get the Penrose inequality. Later, with joint work with Lesord and Professor Yao, we find some conditions on the initial data set that if you impose that, you can get this alpha equal 1 case. And we prove that, and we call that admissible, initial data set. What about the Hooke conjecture? With Lesord and Yao, we study this, and again for the admissible initial data set, and we prove we come up with a new definition of mass in terms of the domain omega and something which is called the Jang graph, which I will come to this at the end of this talk. This quantity is very similar to the quantity that Shitan defined, but it's based on minimizing hole in the Jang graph. So if you have this inequality, we prove that there's a MOTS. There's a MOTS in your domain, okay? So it's a version of the Hooke conjecture. So all of these results also hold for Wang-Yau mass, and this one hold with if and only if a statement about the rigidity. So if the Wang-Yau mass is equal to 0, then if and only if that initial data set arises from Minkowski space. Furthermore, by Chen, Wang, and Yao, they show asymptotic condition of this. So they show that actually when you have a coordinated sphere, then this Wang-Yau converges to the AdM mass. They even show more about the energy and momentum, the same kind of result. Also, they study in the null infinity, and they show that actually it converges to Bondi mass. So it has most of the properties that they mentioned. This quasi-local mass actually have that. Nobody studied the stability. So that's an open problem to study the stability of these two quasi-local mass for initial data set. So stability of the rigidity. Let's say you have a sequence of initial data set and Liu-Yau mass or Wang-Yau mass converges to 0. What can you say about the limiting, initial data set? Is it like an initial data set from Minkowski space or not? So what will happen about the static case? So you can, up to here, the reference is Minkowski. And the reason for reference to be Minkowski is you have like a 0 mass over there, okay? And you have this kind of beautiful notion of isometric embedding. You only need to assume the Gauss curvature is positive, then you can get this kind of isometric embedding, and you can define your Hamiltonian of the reference, and then the difference of the Hamiltonian will give you quasi-local mass. So you can change the reference with the static to a static reference. And what is a static spacetime or static reference for our talk? It's actually a stationary spacetime. A stationary spacetime is a spacetime which have a time-like Killing vector field. And the static is that time-like vector field is furthermore is like upper surface orthogonal. And that will end in the local coordinate. You can write down the metric looks like this. And you can say the Einstein equation also breaks down to these two equations. And you can say the triple, the manifold of the constant time, hypersurface, and the metric G and the function V are solutions of these two equations. So in that case, we call that, static manifold, which is sitting in the static spacetime. So there are examples of this. The first trivial example is Minkowski, V equal 1, and that's one solution. The next one is like Schwarzschild manifold, is another static one. So Schwarzschild manifold is like the manifold is like an interval times a sphere. The metric looks like this. So you have this function V, which we call that the static potential, and then you have like this sphere, and the static potential is the famous 1 minus 2m over r. And you can change that to AdS space. That's another static one. But note that here the cosmological constant is -3 in this equation. And then the static potential is just 1 plus r squared. And the manifold is a hyperbolic H3. And finally, you can also have like AdS Schwarzschild. And in the AdS Schwarzschild, the static potential is 1 minus 2m r over r plus r squared. And as you can see, the scalar curvature here are in the hyperbolic setting is like -6 or 2 lambda. Okay. So what is the static quasi-local mass? So static quasi-local mass is like you still need to define a Hamiltonian, and the Hamiltonian of the physical space, when you have just a Riemannian manifold like omega and G, it's just the integral of the static potential times the mean curvature. So this is the Hamiltonian for Hamiltonian is just VH or minus VH for the physical space. And Hamiltonian of the reference will be like minus V, the mean curvature of the surface in the static space. Note that here we don't have a general result about isometric embedding in an arbitrary static reference. We need to prove that. So defining a static quasi-local mass is tied to the problem for isometric embedding in the static spacetime. If you can define it with some properties, then you can actually go ahead and define this quasi-local masses. So that's the assumption you need to impose, that there is isometric embedding in your static manifold. So this is called the Brown-York, static Brown-York mass. You can similarly define, as you can see, the difference is this function V. You can similarly define for the initial data set, the static Liu-Yau mass. And the static Liu-Yau mass is you have the mean curvature of the surface in the static space, and also here is the mean curvature vector in the physical space, and you have this static potential V. Okay. So as we discussed before, this Liu-Yau mass is only addressing the trivial isometric embedding. So you have, let's say, your initial data set, something like this, and you do isometric embedding, and this is your M, G, and V, which is sitting in a bold M, which is your static manifold, and you only do like a trivial isometric embedding in this constant time slice. You don't do a general isometric embedding in the space-time. So you expect a similar kind of result also hold for this one. This one seems to be too much positive, but there are a general result. So Chen, Wang, and Yau, they actually extend this definition of Wang-Yau mass to the static reference. They first address the cases of de Sitter space and anti-de Sitter space, and then they extend it to arbitrary static reference. And everything is based on assumption of existence of generalized metric embedding, you know. So this is a kind of assumption in our problem, and we will highlight that when we go to our result. Any questions so far? Okay. So note that what is this static quasi-local mass? So let's say your static reference has more energy than your physical reference. So when you are comparing your Hamiltonian, this kind of difference, which you call that the static quasi-local mass, can be negative. So that's a problem with this definition. So you don't have a notion of positivity like doing the isometric embedding in the Minkowski space. If you do isometric embedding in the de Sitter and AdS space, yeah, they have zero mass. So you expect that the static quasi-local mass is still to be non-negative. But if the target is Schwarzschild or AdS Schwarzschild, then you need to revise this statement of the positive mass conjecture. And the statement is actually the quasi-local mass, whatever you have, a static quasi-local mass, plus the mass of the reference should be non-negative. And that's the true conjecture for, you know, positive mass theorem. The first time I actually discussed this was with Muta Wang, and he actually explained this to me that's the reason behind this. And that was the start of this project. So now let's just try to see this. Let's take a sphere in a Schwarzschild. Okay, let's take a sphere in a Schwarzschild with radius r and with the mass m. So that's our first Schwarzschild, like something like this. And this is our sphere. And this is a Schwarzschild with mass m. And do isometric embedding to another Schwarzschild with the bold m, mass bold m, and you embed it like S of r. Then you start to compute the static Born-York mass. And then you start to compute, you get the difference of these two masses, and plus some decay. So this is also a kind of example for this conjecture. Now you can say, okay, you are having a horizon. So let's just add this m to both sides of this capital M, or the mass of the reference, to both sides of this equation. So add it here and also add it over there. So it's m minus a bold m, and this is supposed to be bold m. Then you get this, and the right hand side is just the mass of the reference, and you know the mass of the reference is equal to the square root of area over 16 pi, because that's the Schwarzschild. So this will motivate a Penrose inequality. So Penrose inequality for a static quasi-local mass is this quantity bigger than square root of the area over 16 pi. So that's a conjecture Penrose inequality. And let's see if we can get a similar result. So there is a result. There's a beautiful result by Liu and Wang-Yau. So the reference here is Schwarzschild. So they have.
Sorry, can I ask a question on the last slide, please?
Sure.
I just want to. You have the bold M is the mass of the static
Reference.
reference, and then
Yeah.
the lighter colored M is the mass of the Schwarzschild, which is not considered the static reference.
No, you have two Schwarzschild. One is the physical one, one is the reference one. From physical one, you pick a surface, coordinate a sphere.
I see. Okay, no
And
problem.
ask yourself, what is the static quasi-local mass of that with respect to that reference?
Okay, thanks.
Thank you for the question. So the result of actually Liu and Wang-Yau is as follows. You have a compact Riemannian manifold with a non-negative scalar curvature, and that's our dominant energy condition. And it has two boundaries. One of them is like sigma h, another one is this sigma. And you assume that sigma h is a horizon, so it's a minimal surface. And the sigma has a positive mean curvature. And you assume there is an isometric embedding of this sigma in a Schwarzschild. This is a Schwarzschild with a mass m, with some property. One of the properties is the Ricci curvature in the normal direction is actually negative. And also it's like two convex and a star shape. So you put some conditions. And note that we don't know the existence of isometric embedding. There are some results by Lin and Wang and also Miao and other people about the isometric embedding. But one thing we should know is like the uniqueness actually does not hold. Like there are also results by Poning-Chen about this, that you need to, in addition to get the uniqueness about the isometric embedding, you need to actually fix the mean curvature too. So there's one extra assumption. Anyway, if you have this setting and if the isometric embedding actually exists, they prove that the Riemannian Penrose inequality. And later they study like the rigidity case, and they show actually the rigidity hold. So the equality hold if and only if this compact manifold is isometric to a bounded domain in Schwarzschild, which enclose actually the horizon. So we extend this to the initial data set, and we prove like a similar result for Liu-Yau mass, also for Wang-Yau mass. And we assume there's isometric embedding with different conditions about that isometric embedding. So all of these above conditions hold. Furthermore, if you go to the Wang-Yau mass, you need to have admissible time function too. So you have an initial data set with the dominant energy condition in the boundary, which you want to compute the static quasi-local mass, and you have a horizon, which is a MOTS in this case. Then you can prove actually there exists a constant independent of the area of horizon, and the following inequality hold. No, the same story. We cannot estimate alpha. So if alpha is 1, great, we're done. We proved the Penrose inequality. But we could not actually estimate that alpha. Okay, so let's just try to go to our main result. Main result is the reference. Now we are trying to fix that to be AdS or AdS Schwarzschild. So let's state the AdS case. So if you have a compact like Riemannian manifold with non-negative scalar curvature, and the boundary is like has a ghost curvature lower bound -1 and positive mean curvature, then there's a famous result of Pogorelov about the isometric embedding in the hyperbolic space. And you can get a unique isometric embedding as long as you have this lower bound on the ghost curvature. So we can easily define the static quasi-local mass with the reference of AdS for the Wang-Yau static quasi-local mass. And Wang and Yau in their paper in 2007, before the general definition of quasi-local mass, they prove this quantity is not negative. And furthermore, Shi and Tam, they prove actually the rigidity case. The rigidity hold if and only if the domain is a bounded region in the hyperbolic space, which is the constant time, hypersurface of the AdS. So what will happen if you change that to static Liu-Yau mass? And here is our first main result. So let's say you have an initial data set with the dominant energy condition. and the boundary has a ghost curvature lower bound -1. So we know there is isometric embedding on the hyperbolic space, which is sitting in the AdS space. So then we prove that the static Liu-Yau mass is non-negative. Furthermore, we show that if it is 0, then the initial data set arises from AdS. But we did one step, more than that. So there is a result by Lin and Wang, and they try to repeat the same isometric embedding, the general isometric embedding of Wang and Yau, and they prove there is a general isometric embedding with the time functions like tau in the AdS space. So when you have this general isometric embedding, then you can use the general, Chen, Wang, Yau static quasi-local mass. And we actually prove a similar result for that, plus the rigidity case with the if and only if. Okay, so the next result is, let's change the target. Let's make the target to be AdS Schwarzschild. Now this time, we need to assume there is isometric embedding. So assume there is isometric embedding of your manifold to Schwarzschild space, which is a star shape, 2 convex, and also the Ricci curvature has an upper bound -2 this time. So in the Schwarzschild reference, the Ricci curvature was -0. Here is the upper bound is -2. Then this is our other result, which says if you have a compact Riemannian manifold with a scalar curvature lower bound, -6, and the boundary of your domain has positive mean curvature and have this assumption, then one can prove the positive mass conjecture for a static Bohm-York mass. So we can go one step further and state the result for initial data set. So we prove the Riemannian setting. We also prove the general initial data set. Okay, so let's try to give you a sketch of proof. And I'm going to only prove the theorem 3. So theorem 1 and 2 are similar, so I'll give only the proof of theorem 3. Okay. So I should say that theorem 3 also holds for Chen, Wang, Yau quasi-local mass with the reference of AdS Schwarzschild, assuming there exists isometric embedding. So here is the sketch of proof. There are 4 steps I'm going to discuss, and we use these 4 steps to actually make the proof work. At the beginning, we try to different techniques, but actually we're forced to solve a differential equation, which at the beginning we try not to, but at the end we forced to solve that to get this result. So the step 1 is solving a Jang static potential deformation. You add Jang static potential equation. Step 2 is to construct extension, which is famous extension of Bartnik-Sheehan, but now we construct a static Bartnik-Sheehan, so with the potential. Then we glue them all together. So in step 1, we have, let me go to the last one, and finally we find the lower bound. So let me just try to, before go to the detail, let me go to give you some ideas. So we have our domain. This is our initial data set. We solve a differential equation, a static Jang equation, and then we get another manifold, which is a graph over this one. Let's call that omega bar G bar, and with the function phi. And function phi is the solution of the static equation, which is coupled to the Jang equation. Then we know the isometric embedding of this. These two has the same metric, but different mean curvature. We do, by assumption, we have isometric embedding in the AdS Schwarzschild. We construct the extension, asymptotically hyperbolic one, with the scalar curvature -6, and we also this extension, it has the manifold, it has the metric, and also it has a static potential, phi plus. So phi plus is also a solution of a static equation. Sorry. Then we glue them, and after gluing, we use the result of a Spinora proof of the positive mass theorem to show some quantity is positive, and then we also show some monotonicity for some quantity from here to infinity. And altogether, when you combine all of them, you get the proof. So you need to glue not the manifold. In addition to manifold, you need to glue the initial data set plus the static potential. So you need to glue everything. Okay, so let's just go to the proof. So pick an initial data set. As we know, the initial data set has the dominant energy condition, so you don't have this scalar curvature bigger than -6. Now you need to boost the scalar curvature to make it to have at least distributionally this condition. So we consider a Jang graph, a graph over our initial data set, which the height function of the graph at the boundary is just 0. And we assume this graph is in this product space, p squared dt plus g. So this is our graph, and you can compute the metric of the graph. It looks like this, and you can compute the second fundamental of the graph, which looks like this. Okay. Now, we are not picking any graph. We are picking a graph which is a solution of a coupled system. So a graph is a solution of the following coupled system. I write that in a compact form. So the first equation is the famous, generalized Jang equation introduced by Bray and Curie. With the boundary condition, I'm putting tau, but in this talk, tau is equal to 0. For Chen Wang-Yau quasi-local mass, tau is not 0. And then you have this static potential equation with the boundary condition that the phi should be equal to the static potential of the Schwarzschild for our reference. Now, what we know about this system is first that the first equation, as I said, is generalized Jang equation. And this generalized Jang equation is a generalization of the result of Schoen and Yau. So if you put phi equal 1, then you get Schoen and Yau. Note that here also I'm changing, to write this equation, I'm changing the second fundamental form. The second fundamental form here in this equation is H, which is the second fundamental form of embedding of the graph in the Lorentzian manifold, not the Riemannian manifold. And there's some technical reason for that. So assuming uniform bond on phi, Han and Curie actually prove there exists a solution for this. And the argument is similar to the argument of Schoen and Yau. So the method is similar. They also study the blow up. Like when it does blow up, it should be a MOTS. So that's something extra. So, but you need a uniform bound on phi, and that's all you need. So, okay, let's go to our main result for this part, the step 1. The step 1 is actually, the main result is we apply a fixed point, procedure to prove the existence of a solution. So let's say you have an initial data set. It's the boundaries on trap, and there is no horizon, no MOTS inside. Then this coupled Jang static potential has a solution. And the idea is as follows. You pick a closed convex subset of this Banach space H1 and C0, and you construct a map, which this map is a composition of different maps, continuous and compact, and you get a compact map from S to S. So what is this T0? T0 is a smoothing map, is some sort of modification. T1 is the Jang equation. So as we know, when you're solving the Jang equation, you can get a kind of C3 alpha estimate for the solution. So here, let's say the C2 alpha. And then the T2 map is actually coming from solving the static potential equation. And then you have this inclusion map, which is a compact map from the C2 alpha to this space S. Furthermore, using using the second or the static potential equation, you can get a kind of bounded bound for this phi, which is a composition of all of these maps. And using this bound plus that compactness and continuous property of the map, you can apply the Schroeder fixed point theorem. And you can show there is actually a solution. The solution is in the weak sense. But then you use the regularity condition of the PDE, and you show that actually the solution is smooth. So in step 2, you started with something, let's say psi, but through this argument, you show that the psi is equal to phi, and by regularity, you know the phi is smooth. And so in the step 1, you're actually solving the coupled system. Altogether, you get there's a solution. Note that we did not study the blow up. We did not study the uniqueness until now. The work is in progress. So you have now a Jang graph, and actually you have a static Jang graph. So you have a solution of the Jang equation. The nice thing about Jang equation, it boosts the scalar curvature. Now the scalar curvature of the Jang is this part, which is positive by dominant energy condition, this part positive, this part positive. This part will give you the -6, and this part is something extra, which distribution is nice. So now we have this kind of triple. Furthermore, we proved something else. So we proved that actually similar to Yau, Yau has a result about the existence of black hole due to the curvature of the boundary. And similar to that, we proved that this quantity which is showing up in the Jang graph is actually bigger than the norm of the mean curvature vector. So we are going to use that. So this quantity is actually positive if you assume this is a space line, which we are. Now let's go to the step 2. The first step, we know there is isometric embedding. So that's the 3 things we have based on this assumption. Now, there is isometric embedding. We want to construct this extension. So the first step is by Chen and Mao or Liu. They study solutions of an inverse curvature flow with the speed in terms of principal curvature kappa 1 and kappa 2. And if you have these conditions, then they showed actually there is a solutions, and asymptotically this kappa goes to 1. Using this and combining with the assumption, we could show that actually the Ricci curvature condition and also the Gauss curvature lower bound condition also preserve under this flow. So that's something extra nice, which we are going to use that. Now we have a fluation for AdS Schwarzschild. This will give us a fluation because we embedded this surface in the oh, sorry. This is not H. This is M of AdS Schwarzschild. So you have this embedding and you have this fluation. If you add all of these solutions of the flow, you will get a metric which is a different metric for AdS Schwarzschild. Okay. Now we want to actually change that using the trick of Bartnik. So we change it by solving a differential equation. So when you want to change your metric and put an arbitrary function omega here, such that the scalar curvature to be -6, you get a parabolic PDE. And using the condition that k of t has a lower bound -1, you can prove the existence of this parabolic PDE, similar to the result of Bartnik, similar to Xi and Tan, and similar to Liu and Miao. Note that we are assuming the mean curvature. We're picking this metric because we want the mean curvature of this sigma 0, which flow started from that, to be exactly this quantity, h bar minus x of nu bar. And we know this is positive. We already proved that this is bigger than the norm of h, which is positive. So we also studied the uniform, C0 bound, and based on that, in the coordinate, the metric looks like this asymptotically. So the metric is asymptotically hyperbolic, and the decay is really, really strong. Now you need to solve the static equation. You have the Riemannian manifold with the scalar curvature -6. We solve the static equation such that at infinity is like V of S, but if you recall, V of S blew up like R. So now this is not you need to be careful about the asymptotic of your solution. So you need to use the SOP and super solution and prove there exists a solution for this linear PDE. And after solving this, you get the static, this time, Bartnik-Sheetan extension. So you have the Riemannian manifold with the scalar curvature -6, plus you have a function which is a solution of a static potential. Okay, this is step 2. And step 3 is glue it together. So you glue all parts of your data. You glue your second fundamental form, you glue your vector field X, you glue your static potential phi. So you get the following complete, Riemannian manifold. So a scalar curvature here is just -6, and the scalar curvature here is just bigger than -6 minus that dive term. So 2 minus p dive of px. Now we deform it. This gluing is not smooth over that region, so we deform it to make a smooth initial data set. When you deform it, everywhere you have this quantity is non-negative, but also you can show actually in a tubular neighborhood also you have this condition. You don't have this condition, sorry. Except from that tubular neighborhood, everywhere else you have that condition, this tubular neighborhood, which is gluing. You don't know what is the behavior of this quantity. It can be negative or positive. Okay. Now, using this, you deform everything, again, this time with a conformal transformation. So you do conformal transformation to get the scalar curvature -6 everywhere. So we can prove the existence of a smooth, complete, asymptotically flat hyperbolic Riemannian manifold. The metric is a conformal transformation of that gluing and deformation, manifold. The nice thing this time is the scalar curvature everywhere is -6. And the last part is there's a quantity M. I'm going to talk about that in the next slide. But M of this G plus can be written in terms of M of this conformal metric plus something which is positive when you have a sufficiently small delta. Okay, so if you prove this is positive, then we are done. Note that this is a Riemannian manifold. It's complete. It's asymptotically hyperbolic with the scalar curvature -6. So you have everything for the quasi-mass theorem for asymptotically hyperbolic. You have a complete asymptotically hyperbolic Riemannian manifold with the scalar curvature bigger than or equal to -6, which in this case is a -6. So what is this quantity? This quantity is very similar to the static Brown-York mass with respect to the hyperbolic space. What you have, like this M of G plus, is the difference of the mean curvature. The H0 is the mean curvature of the isometric embedding inside the hyperbolic space, and H is the mean curvature with respect to the metric G plus. So if I change G plus to, I don't know, another metric H, then, G bar delta, then here, this mean curvature will be respect to that. Note that we can do always this isometric embedding in the hyperbolic space because all of these fluctuations, they have a lower bound Gauss curvature -1. So when you have this condition while embedding problem, you have this unique isometric embedding in the hyperbolic space. So this definition is well defined for any of these fluctuations. Now, what else we show? The first step, we show that using a spinorial proof, we show that the M of G bar of delta is non-negative. So using the fact that for a small delta, A of delta is also non-negative, you get the M of G plus is positive. And furthermore, you get the M of this quantity for exactly for our G hat metric. What was the G hat metric? G hat metric was psi squared dt squared plus sigma t. So G hat metric was a new fluctuation for the AdS Schwarzschild. And this quantity for this metric is exactly the mass of the target. Okay. And now we go to the last part of our argument. And this is the last part of it. So last part of proof is this. You have your left-hand side. The first term is the quasi-local mass. And the second term is the mass of the target. Based on the thing that we proved, that h bar minus x of nu bar is bigger than the norm of vector field, you get the first inequality. And we have our G plus with the initial metric of H plus, with the initial, sorry, mean curvature of H plus. Let's call that H plus now. Oh, sorry. I'm zooming too much. Okay. Okay. Now, Liu and Miao prove something very interesting. They prove if you pick this quantity under a similar flow that we had, in a static space, even though their paper was about Schwarzschild, but their result was for all static spaces, then you get some monotonicity behavior for this quantity over our extension. So this is decreasing. So as a result, this quantity at sigma 0 is always bigger than the quantity at sigma infinity. But now at this level, you can do something simple. You can add minus h of 0 plus h of 0. And h of 0 is the mean curvature of this sigma 0 embedded in the hyperbolic space. That will give you these two masses. The first one we prove is bigger than this, and the second one we prove is exactly the mass of the target. So as a result, we show that for sufficiently a small delta, this quantity is not negative. And the rigidity, we show that the rigidity does not happen. As we know, the rigidity, we expect it happen for the Penrose inequality, but we don't have a Penrose inequality in the AdS setting. So we don't have the rigidity, but we can show this inequality is actually a strict positivity, because if it is equality, you get a contradiction. And the contradiction goes to the fact of the uniqueness of a spinorial proof and the equality case of a Liu and Miao. If you combine both of them, then you get a contradiction. So this is end of my talk. Thank you for listening.
Thanks, Aghil, for a wonderful talk. So it's time for questions. So if anybody has any questions, so please go ahead.
Thank you.
Sorry, I was muted. Sorry. I do have a question, but I was muted, I realized. Sorry about that. Earlier you had mentioned that let me just find the slide number so you can go back there. Theorem 3, when you first stated it, did you say it also holds for the other quasi-local mass? The
Chen Wang-Yau?
Yeah.
Yeah, it does hold, because the argument of the proof is similar. it does hold, but you need to assume admissible time function, and our admissible time function is slightly different from admissible time function of Wang and Yau, because it's based on one of the conditional admissible time function is this assumption. And,
Yeah.
and another one is like some reduction we did is slightly different, but altogether is like the same. The argument of the proof is similar to that paper of Wang and Yau.
And in that case, you also have difficulty with rigidity?
Yes, okay. When there is a rigidity, so rigidity does not happen because the target is Schwarzschild with a horizon. But we are assuming this initial data does not have a horizon.
Of course, yes.
Yeah, so
yes,
we don't get
course,
rigidity,
right.
but we show that if the rigidity happens, we get a contradiction. Like it cannot. And the reason we are assuming
Right.
horizon,
Oh, okay. There's assumption that there's no horizon.
Yeah, the reason is if you assume there is a horizon, then that coupled system should blow up at the horizon, and then we need to study the blow up. Then we need to study the conformal of the blow up case. And so, what is the area of the blow up related to the area of the mass? So everything, it will be really complicated.
Okay.
And we don't have Penrose inequality. So even if you do all of these cases, the hope is at the end you have a Riemannian Penrose inequality for AdS, but we don't have. So
right.
yeah. Thank you so much for the question.
All right, so if there are no more questions, so let's thank Aghil again for this wonderful talk.
Thank you.
Thank you, everyone.
And let's stop the recording.
Have a good afternoon.